Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Pieter van Dokkum with us today. Hello, Peter.
Hi, how are you doing?
I am doing awesome on this October 7th of 2024 as we record this. And I am in Phoenix. And it is starting to cool
Hmm.
down. We're still hitting triple digits today,
Yeah, I
like
was, I was
around
just about to
1 o'clock or
say it
something.
means it's
So
only 100. Yeah.
yeah, but it is cooling off in the morning, so it's kind of nice. It's getting nicer,
Mhm.
I should say. And how about you, Peter? Where are you located at?
I'm in North Haven, Connecticut.
Okay.
Yeah.
Is
Mm.
trees turning color? Are we starting to get into fall?
It's starting for sure. Yeah, I was in New Mexico yesterday though, so
Oh,
I haven't barely been outside since then.
okay.
Yeah, there the evergreens are still green.
Yes, it's the high desert. Very, very cool. Very nice. And Peter, what do you like to do for research?
I work on a whole bunch of things, nearby diffuse galaxies, stellar populations of galaxies, and also very distant galaxies with JWST. Yeah, a variety of
Cool.
things, really.
Within that, yeah, broadly defined.
Yeah.
Very cool. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free, go get one.
Mhm.
Reconciling ML ratios across cosmic time, a concordance IMF for massive galaxies. And Peter, take us away.
Yeah, this is work I did with a colleague, Charlie Conroy. We've been working on this topic for 14 years now. Yeah, I think the first paper was in
Awesome.
2010.
Wow. Very
Um,
cool.
yeah, we made a bold claim in 2010, namely that the initial mass function of massive galaxies has a form that is different from what it is in the Milky Way.
Okay.
Uh, so the IMF, for those of you who are a little rusty on that topic, is the distribution of stars, the masses of stars when they were formed.
Uh-huh.
And so it tells you for every solar mass star, how many low mass stars do I form and how many high mass stars do I form.
Yes.
And it's a very important function in all sorts of areas of astronomy, of course. And it tells you about star formation, about mass, and about a lot of other interesting things. And back in 2010, we claimed that massive galaxies have this very bottom-heavy IMF.
Right.
Uh,
Okay.
and that led to a lot of discussion back then. And this is sort of the latest update in that long story.
Okay, cool. Very good. All right.
Um, yeah, and so in terms of background, that's sort of the background of the IMF in general,
Uh-huh.
and it's become over the years it's always been an important topic, but it's become very important now with JWST.
Yeah.
And the reason is that all we can see, of course, is the light of the most luminous stars in these very distant galaxies that JWST finds.
Hmm.
And we infer from that how many stars are formed in total. So we find these galaxies at redshift 7, redshift 10. All we see is the light from the O stars and the B stars in these galaxies, very luminous, very hot stars.
Yes.
But the mass in these galaxies, the stellar mass, is all in the lower mass stars.
Uh-huh.
So solar mass stars and half solar mass stars, etc. But you can't
Hmm.
really see them. So you have to assume how many of those stars exist, given the number of bright stars that you can see.
Okay.
And so that's a known problem, but it became a particular issue because JWST found all these very massive galaxies or seemingly massive galaxies
Yes.
at very high redshift. You know, that's a whole topic of its own.
Little red
What
dots and all.
That's right. You know, it's been fabulous, really, all these new discoveries.
Yeah.
And a lot of discussion. Are they AGN? Are they actual galaxies, dominated by stellar light? Very active field. But the central question is, how do you transform the luminosity of these galaxies into a stellar mass? So
Yes.
how do you know how massive these galaxies really are? How many baryons were, how many gas particles, how much gas was turned into stars
Hmm.
in these early galaxies. And so people, after this discovery with JWST, in really its first few months of operation, uh, um, people try to make sense of these observations by tweaking the IMF. And so that's, Steinhardt and others came
Hmm.
up alternative IMFs that overproduce the number of luminous massive stars and
Hmm.
underproduce the number of low mass stars. So
Okay.
what that does is you still reproduce the luminosity of these galaxies just like before, but
Okay.
now the inferred masses are a lot lower because you lower the number of low mass stars, and
Uh-huh.
all of the stellar mass is locked up in these little stars,
More
not in the
heavy.
bright stars that
Right.
are more easily detectable. So that's been a solution that's been proposed essentially for these seemingly massive galaxies at early times.
Hmm.
And and we know it's possible to make such IMFs. So that's the central star clusters in the Milky Way have an excess of high mass stars, it seems, compared to the general IMF in the Milky Way.
Okay.
And so there's a cluster in the Magellanic Cloud, 30 Doradus, which seems to have that as well.
Yeah.
And there's also theory, that says, okay, you can do that, by changing the gene's mass in particular to
Right.
higher masses.
Hmm.
So far so good, except for this observation by Charlie and myself in 2010, and a lot of other work that accumulated over the years, which found that nearby elliptical galaxies, which we think are the descendants of these very early galaxies that we see with JWST,
Uh-huh.
when we look at the IMF in these nearby massive galaxies, we find an excess of low mass stars compared to the Milky Way.
Okay.
So it's essentially the opposite of what you would expect from
Yeah.
these JWST observations.
Hmm.
So compared to the Milky Way, what we see in the local universe is a bottom-heavy IMF with a lot of low mass stars and extra mass
Yes.
compared to the Milky Way. And what is needed, it seems, at high redshift is a bottom light IMF with less low mass stars compared to the Milky Way.
Okay.
So we're in this sort of awkward situation where, if anything, if we believe this whole story of these massive galaxies, Redshift 7, turning into massive galaxies today,
Yeah.
that we've exacerbated the problem because, if anything, there should be more mass in these Redshift 7 galaxies locked up in these low mass stars, not
Okay.
less.
Okay.
All right.
I'm with you. Uh-huh.
Yeah. So anyway, so that's where we kind of are, and and then the paper goes on to talk about massive galaxies at redshift 2 to 5, sort of in between, and they seem to be sort of in between in other ways, not just in redshift, but also people have studied their dynamical masses of these galaxies. And from the dynamical mass, you can infer what the maximum stellar mass is in these galaxies.
Okay.
You have dark matter, gas, and stars in
Yes.
galaxies.
Hmm.
And then you can measure the total mass from the dynamics. If you compare that then to the stellar mass that you infer with a particular initial mass function, you
Okay.
can get some kind of limit on what the initial mass function can be. And what people find there is that
Yeah.
seems more or less like the Milky Way.
Okay.
So there's not much evidence for a bottom-heavy IMF at redshift 2 to 5.
Okay.
So we have, if you then sort of back up, we have at redshift 0, it seems galaxies are bottom-heavy, these
Yes.
massive galaxies. If you go out in redshift, sort of, redshift 2 to 5, they seem to be more or less Milky Way, the IMF. And what
Okay.
we'd like at high redshift, very high redshift, redshift 8, 9, 10, is actually bottom light, so lower mass than the Milky Way.
Okay.
But that's all seems very contradictory because everybody believes, including that's the assumption in this paper, that all these stars were formed, very early on at redshift 7 or 8,
Okay.
and so they should all be the same. The IMF can't change because the stars have all formed early on, and we're just measuring how many stars there are in galaxies that we think are directly connected evolutionary.
Yes. Okay.
So they should all give the same answer, and seemingly they don't.
We
You
have
know,
a
we,
mystery. We have a
we
mystery.
have a mystery, right?
I like mystery.
And one solution is to invoke complex formation histories.
Ah,
That
yes.
maybe there was star formation late. Maybe something complicated happened, but that's sort of an unsatisfactory way out. And so what we do in this paper is different. We try to come up with an initial mass function that fits all these constraints.
Okay. Okay.
So we say, let's forget physics for a moment.
Okay.
Let's just assume functional forms of the initial mass function that are essentially, free to vary in a particular with a particular set of constraints. And then what IMF could potentially satisfy all these seemingly contradictory constraints? What form
Very
of the
cool.
IMF?
And we'll give a
Um,
shout out to Beatrice there. Yay.
Yeah, absolutely. Yeah, we have a conference in her honor later this month
Oh,
at
very
Yale.
cool. Very cool.
Yeah, on early JWST results.
Yeah.
And yeah, she was it's unbelievable when you read the Tinsley papers, how visionary she was. And many things can be traced back to her work,
Nice.
including this work.
Yes.
Um, Anyways, so yeah, the methodology, I sort of hinted at that already. We assume a particular family of IMF shapes
Okay.
in this paper, and they are illustrated in Figure 1. If we
Yeah,
can
let's go to figure one. Let's
do that,
get
yeah,
here. And there we go.
Fiber figure.
Whoops, wrong way.
No,
Okay,
that's
pull
good.
that up. There we go.
Yeah. So. Okay, this shows a bunch of different IMFs, forms of the IMF. So the blue line is just a straight line. That's the Salpeter IMF,
It is.
which is 1955. Now Salpeter only measured it above one solar mass, so we tend to just assume that the Salpeter IMF was introduced like this in 1955, but it's shorthand for saying simple power law all the way from low masses to high masses.
Indeed.
So this goes from zero point 0.1 to ultimately to 100 solar masses, but I'm focusing here on the region up to about 5 solar masses.
Okay.
And then there's the Krupa and
Yes.
Chabrier IMFs, which
Yes.
are the forms that fit the Milky Way clusters well. So a typical star cluster in the Milky Way has an IMF that looks like that. So a power law above sort of 1 solar mass,
Yeah.
with a slope similar to salpeter, but then a turnover. So a turnover at lower masses with a sort of a peak at a couple of tenths or 1/10 of a solar mass.
Yeah.
And both forms are functionally, the functional form is different, but they are functionally, sort of in practice, essentially the same. They give very similar results.
Mm-hmm.
And so those are the standard IMFs that everybody uses, including the people who get masses for JWST galaxies at redshift 10. They assume either group power Chabrier to infer the total mass.
Mm-hmm.
So the IMFs that we're exploring in this paper are indicated by the dashed line.
Diesel.
So they are steep at low masses, as steep as
Like,
salpeter or even steeper.
yeah.
That's the high masses.
Yes.
Yep,
Mm-hmm.
there.
Yep. Yep.
Steep
Yep.
at low masses.
I'm with
That's
you.
right.
Mm-hmm.
And so that's to explain the results for nearby elliptical galaxies, where we see that there's an excess of low mass stars.
Okay.
But then it's flat at high masses. So at beyond 1 solar mass, it's actually flatter than both salpeter and the Krupa and Chabrier functions.
Yes.
Uh, so, so it's top heavy. That is, there's an excess of massive stars in this
Mm-hmm.
IMF, more massive stars than standard IMFs compared to the number of 1 solar mass stars, but also bottom heavy. So both bottom heavy and top heavy.
Okay.
So we call these key slope IMFs because it's sort of, you kind of start steep and then start with the black slope and then you go to the blue slopes and then to the green slopes at the bottom.
Very cool.
And that's the family of IMFs that we're exploring. And the limiting case is simply the salpeter IMF,
Sure.
just the same slope and the
Boom,
same
boom, boom. Gamma one
right.
equals gamma
But
two.
then we say, okay, if we make it look more like this, what do we get? Can we fit the constraints? And the idea was simply like, okay, we need bottom heavy and we need top heavy. And we need top heavy at these high redshifts where we see these massive stars. And we
Yes.
need bottom heavy at low redshifts where the only stars that are surviving are low mass stars. So
Okay.
it might work. It's sort of like the regimes where we measure these things are different. Like at high redshift, different stars dominate the light than at low redshift. So it may be that we can get a consistent solution for these
Oh,
different observations.
very nice. Okay, I'm with you.
Yeah. Okay. So let's look at the methodology again. We don't have to go through that in its entirety, but
Whatever you like.
um,
Let's see. Yeah, I think we
yeah. So that's
kind of
the
said,
one, two, three. That basically
yep.
describes what I was saying,
Okay. Yeah,
illustrating.
and saltpeter is gamma 1 equal gamma 2 equal
Mm,
zero point 0.3.
yeah.
Yep. Mm-hmm. Okay.
Yeah, and then the observational constraints, it's more or less what I said. We have a few, if you can keep scrolling to the actual equations
Oh, here we go.
there.
Yeah, yeah, yeah. Here we go.
Yeah.
Okay.
Yeah, this is
Okay.
perfect. So the observational constraints are this parameterized with this parameter alpha,
Mm-hmm.
the mass excess of the IMF, and it's essentially the mass that's the mass of the IMF for a particular IMF given a certain luminosity. So it's the mass to light ratio. How much mass do you have given the light that you see?
Yes.
Divided by the mass to light ratio that you would get for a Milky Way IMF.
Uh-huh. Uh-huh.
So if this parameter is 2, you have twice as much mass than in the Milky Way IMF. If it's a half, it's half the mass of the Milky Way IMF.
Okay.
Okay, so that's the common definition in this field for parameterizing different IMFs.
Okay.
It's in terms of its stellar mass. And then we have these three constraints, and there's this particular distinction with living and total.
Yeah, I was gonna say we got libs and totes here. Uh-huh.
Yeah, so that's a little bit subtle, but it is important because living is the stars that are still around at the time of observation.
Okay.
So an elliptical galaxy today, the only stars that are still around have a mass up to about zero point 0.9 solar masses.
Mm-hmm.
All the more massive stars have died at this point because these galaxies are very old. They're 10 billion years old.
Yes.
And whereas at redshift 10, those stars much more massive are still around.
Gotcha.
Star-forming galaxies have stars up to 100 solar masses, that are still around. And so there, the light is dominated by these much more massive stars. So that's living. The total mass to light ratio includes the mass of remnants. So when a star dies, it becomes a black hole or a neutron star or a white dwarf,
There we go.
one of those things, which also has some mass, obviously. It's not like the mass is all gone after the supernova.
No.
And the alpha tot includes that mass.
Got
And
it.
so that's the mass that's relevant for, say, dynamics, right? When you are sensitive to all the mass, you don't care if it's in the form of living stars or living stars plus neutron stars and all the other things. It's just
Right.
everything.
Okay.
So those are so we have these particular constraints, and the top one here says you have to have a whole bunch of mass in these low mass stars that are
Yep.
still living. That's from
Okay.
the all the IMF results on elliptical galaxies.
Uh-huh.
Um, the second one says for these nearby elliptical galaxies, the total mass can't be too high because otherwise the dynamical constraints would not be
Not
satisfied.
satisfied. Yes. Okay.
Yeah, so it's sort of in this sort of limited range of between 1.6 for living and 2.3 for the alpha tot. Essentially, you want them to be about twice as massive as for Milky Way IMF, but not more massive.
Yes.
You can't overproduce remnants, is what this says. Which you could do with certain IMFs. And then the third one is simply that at higher redshift, the total mass to light ratio can't be too high because of these dynamical constraints. That people say, hey, it kind of looks like the Milky Way IMF
Mhm.
based on the dynamics.
Okay.
Uh,
Yes.
and so that's it. And then what we did was simply vary these IMFs, these three slopes, over a huge grid of different slopes, and
Okay.
ask for each of these slopes and for a given age, what is the effective mass to light ratio, compared to the Milky Way.
Yes.
So
Okay.
that exercise is actually it's not a fit to data. It's just saying what IMFs satisfy this particular set of constraints, if any, right?
Right. So we're going to have
Ah,
some probably that are in range and some that are out of range.
that's right. That's right. And so that's section 3.1 and figure 2. that shows.
Ah, I jumped the gun. Okay, here we
Yeah,
are.
there we are.
Yes.
Yeah, so my co-author, esteemed Professor Conroy, didn't like this plot very much. And if your
Sure.
co-author doesn't like it, I'm not going to try to make anyone else like it. But essentially, what this shows is in this three-dimensional plot of these three pieces of the IMF, these three sections of slope,
Uh-huh.
um, gamma 1, 2, and 3, what IMFs are allowed for these three different constraints. The alpha living today, the alpha tot today, and the
Yes.
alpha tot at
Nope.
high redshift.
I'm with you.
And green is good and red is bad.
Good.
So
Okay.
that's the idea. So where
And
it's green, it's allowed, and where it's red, it's not allowed.
and do you want people to note there's a flip here? Green on the
Yeah,
green,
that's on purpose
green on the
because
left.
the
Yep.
alpha tot was an upper limit for the second one, and
Yep.
so it couldn't be higher than a certain number, and for the third. So that's to make the plot sort of consistent. Whereas for alpha living, it was a lower limit, and so then it goes from red to green. Yeah. See, it may make sense to you. It also makes sense to me. Anyway, it doesn't matter. The point is, in this whole parameter space, what you're looking for is a region where it's green in every
Correct.
plot,
Yes.
in both in all three panels, and it's that there is indeed a region. Yep, very good.
No, no, no. All green.
Yeah, where
Just
you satisfy all three
well, you
constraints.
still got some in here, this region up here too.
Yeah. It's also how green is green,
Yeah, exactly.
light green. So see, that's where it gets a little. But
Green,
anyway,
green pea
uh,
galaxies. Okay, there you go.
yeah. So it is possible. And yeah. So if we now
Okay.
scroll down,
Yep.
I think we'll get to the yeah. So there we are.
Concordance.
So we have 20 viable IMFs in this
Okay.
parameter space,
Okay.
where we skip by 1.1 in these three parameters over this grid. And they're all pretty similar. And if you then simply take the mean of those 20 viable IMFs, for these three parameters, you get this, a slope of 2.4 at low masses, where 2.3 is salpeter, so very
Okay.
close to salpeter.
Right.
And then 2.0 in this intermediate mass regime from zero point 0.5 to 1 solar masses, this little piece in the middle. And then for gamma 3, it's 1.9, again, where 2.3 is salpeter. So it goes up quite a bit compared to the salpeter IMF.
Yeah.
And so there is a solution, and so we can see what that solution looks like in the next figure.
Okay. And we will do a double shot here and zoom in as need be. Concordance here. Okay.
Yeah. Yeah, we call it concordance just because it's not really a fit, but it's something that fits multiple constraints from different data sets.
Right.
So, you
hmm
know,
hmm
stealing a bit from the cosmology.
I knew that was coming. And the SNA folks. Yeah, yeah, yeah.
I don't know. Yeah. Maybe we should just
It's a
discuss
good
this
word.
stuff.
I like it. It's a good word.
Yeah. So yeah,
Okay.
the IMF that we then propose is in the top there with these three parameters, and you can see it's pretty close to the blue line, which is the salpeter IMF, but then it turns up at
Yeah.
high masses. And it's a little bit steeper at low masses. Mostly, it's a lot steeper than the Milky Way IMF at low masses. Which
Yes.
is needed for these IMF constraints in elliptical galaxies. And then in the bottom plot, it's the exact same information, except that we multiplied the
Right.
vertical axis by mass.
Sure.
That's just to make it more easily visible, the differences between the IMFs.
hmm
And so you can see it has this very peculiar, shape compared to other IMFs in this figure.
Indeed. Yeah.
Yeah, it's like a factor of four more low mass stars than the
Yeah.
standard Milky Way IMF. So it
And
predicts all this.
the gray air bars here represent the span of those 20 models.
Yep, that's right.
Okay.
Yep. And
I'm with
so, that just says this is 68% of the models that fit.
you. Okay.
Yeah.
I'm with you.
Yeah. So that's the key. The key result of the paper. There is an IMF that fits all these things.
Nice.
And then if we scroll to the next figure, I guess. at this point.
Sure. We're doing some dynamical stuff there and figure three, and we go down to figure four and
Yeah,
build.
this one.
There we go.
So what this then shows is for this IMF, we've calculated these values of alpha, for particular ages, right? But now that we have the IMF, we can also calculate the mass to light ratio as a function of age, just to say like, okay, so how does it then sort of work out?
Mhm.
And so on the left panel, you can see the for a standard IMF, group IMF, which is the IMF in the Milky Way, the mass to light ratio in the R band as a function of age. Okay, it has a particular form. Very young ages, you have a lot of light, so the mass to light ratio is very low. And
Yeah.
then for old ages, on the other side, then you have a very high mass to light ratio because all the luminous stars have died, and you're just left with low mass stars. And so
Okay.
you see the same behavior for the concordance IMF, but the overall slope is different. And so that's sort of the key thing, the key feature, if you will, of this IMF. And so at young ages, what's happening is because it's top heavy, it has extra light in massive stars that
Yes.
don't contribute a whole lot to the overall mass. You get these relatively low mass to light ratios. So
Yeah.
you're dividing by a lot of light that's caused by this
That's
excess of
it. Yes.
massive stars. And so the concordance IMF is below the Milky Way IMF. Mass to light ratios are lower, which is great. That's what we wanted for the JWST galaxies. We
Mhm.
wanted their masses to be as low as possible to not, mess up cosmology
Right.
and our understanding of galaxy formation. So that works in the right direction at very young ages.
Right.
And then you see a crossover point and sort of more or less equal mass to light ratios as the group IMF for ages of, zero point 0.1 to 1 gigayear or so, which
Thereabouts.
is this epoch where we see young quiescent massive galaxies at redshift 5 and 4, this sort of intermediate regime where we had these indications
Right.
that the mass to light ratios are close to that of the Milky Way.
Right.
So that happens there. And
Yep.
then when you go to older ages, so elliptical galaxies in the nearby universe, concordance IMF is above
Yep.
the Milky Way IMF because what we now have is all these low mass stars that become the relevant factor, and there's this huge excess of these low mass stars.
Hmm. Let me ask you a
So
question. This might be minor,
yeah.
but why is there a kink around one in all of them?
Oh my God, I so hope you wouldn't ask that.
Oh, I'm sorry. Oh, okay. What's that kink doing there?
Yeah, I'm not sure. Yeah, I kept meaning to look into that.
Okay.
I suspect, but I don't know. It may be related to one of the kinks in the IMF.
Yeah, the change in slope.
That
Yeah, yeah.
that this is where you go through the kink at one solar mass, sort of where those stars are dying, and so you get a sudden change in the slope of the IMF, and that reflects there. Because
Yeah.
we modify it by this we model it by this particular form. And so in that case, it's almost certainly an artifact of
I would.
our simplistic
Yeah.
power laws.
That
The
does
more
look good.
interesting version is that it's something in the stellar population synthesis model that we use. But I can't imagine what would happen at 1 gigayear,
Mhm.
that is discrete like that.
Yeah.
Uh,
Okay. Sorry.
yeah. No, no, that's funny because every time I look at that plot, I'm like, I should really figure out what that kink is.
Wait for yeah. Next time,
And
next
then
time.
I forget it instantly. So
Good.
yeah.
Good.
Anyway, I think it's just to do with our parameter, our discrete parameterization. But
Fair enough. Fair enough.
yeah. Anyway, so on the right, that's the same information as on the left, except now we've divided those two curves.
Mm-hmm.
So that's this alpha parameter, which is the mass to light ratio
Yes.
compared to the mass to light ratio of the Milky Way.
Mm-hmm.
And so you see this behavior that's compared to the Krupa IMF, which is this horizontal line at zero. And, we have this point where they basically cross over, that line. And then for younger ages, we have lower masses, and
Hmm.
for older ages, we have higher masses,
Right.
up to and
Very
even
cool.
above the salpeter function.
Very cool.
So it does what we want it to do, which is nice. We sort
Okay.
of set it up that way, of course.
Right. Yeah.
Um,
Just because we ignored physics, we were just going.
yeah, we'll get to the physics in a little bit, but
Yay.
yeah, well, somewhat. But before that, this is all done assuming that all massive galaxies behave the same. That there is something like here you have a Milky Way galaxy, here you have a massive galaxy. This is the massive galaxy, this is the Milky Way galaxy. But of course, there's a continuum. Galaxies have all sorts of masses and all sorts of properties.
Right.
And so in the final figure, we
Okay.
um, we take
Yes.
it one step further, and
Ew.
that is
Dispersions. Okay.
yeah. So now we express the results as a function of velocity dispersion, and so we're going to define the IMF not as a constant function that's the same for all galaxies, but as something that smoothly varies from between the Krupa IMF for Milky Way mass galaxies to this concordance IMF for galaxies with a velocity dispersion of about 300 kilometers per second. And then we
Okay.
smoothly interpolate between them. And so that's done. That's illustrated here. That up to 160 kilometers per second, we assume that it's the group IMF. That's right. And
Yep.
then beyond that, you get this divergence,
Uh,
and it's then age dependent. The alpha parameter is age
yeah.
dependent, as we saw in the previous plot.
Right, as it must be. Yep. Yes.
Yeah. So this allows us then for any galaxy to say this is the proper mass to light ratio to use. You don't have to decide what it is, except you have to estimate its velocity dispersion. But then, given its age and its velocity dispersion, this will tell you the mass to light ratio.
Right. And these
Um,
are measured data.
yeah, so those are points from this is a paper by
Oh, here we
Charlie
go.
and myself again.
Yep.
Yeah, where we measured the IMF from
Okay.
these very subtle gravity sensitive absorption features in elliptical galaxies as
Cool.
a function of dispersion. And so we found that it depends on dispersion, and other people have found this too. It's not just us.
Right on.
Uh, and showed that there's this gradual increase in the IMF as a function
Right.
of dispersion. Whether dispersion is the actual physical driving parameter or not is a bit unclear, because everything correlates with dispersion, metallicity and a lot of other parameters.
Yep.
But in practice, this is what's seen. So it's the red curve should correspond to the dots, and then the other curves, of course, have not been measured. You would have to do that at high redshift, if you wanted a direct IMF measurement.
Right. Very cool.
Um, so that's essentially it. And so in the discussion, we try to put some context on the whole thing.
Okay.
Uh, let's see where the discussion
Let's see where we
starts.
start. I think we start up here. Here we go. It is possible.
Oh, yeah, okay. Yeah, so we first say it works.
Yep. Okay.
That's good.
Good. Good.
And then we say it also works if you take into account that galaxies evolve in complex ways. That's the next paragraph.
Mhm.
Uh, Insensitive to progenitor bias.
Yes.
And then if we scroll further,
That. And okay.
um, and
Yep.
uh-huh. So this is all, yeah, we actually tested it out on a few actual galaxies between redshift 7 and 8
Okay.
to fit it with the concordance IMF
Uh-huh.
because, this is all just in model land, the whole paper essentially.
Yeah. Yeah.
But we were wondering what happens if you fit an actual, real life galaxy, so actual photometry of a galaxy with this IMF.
Okay.
And sure enough, you get a mass out of it for that galaxy that is lower than the standard mass that people produce.
Cool.
So a redshift 7 galaxy, if you fit it with this IMF, you'll get a lower mass. And interestingly, the effect was a little larger than what we expected just based on our simple model plot.
Okay.
And that's because it's not just the mass to light ratio that changes. You also change the predicted colors of the galaxy. If you change the number of these massive stars compared to solar mass stars, the colors will also be slightly different. And
Yes.
so the only way to figure out full effect is to fit galaxy photometry and then with these IMFs and say, okay, this is the mass that comes out.
Got it.
And so that's a very obvious next step is to fit, galaxies and to see what comes out. We did it for three here. Bing Ji Wang kindly did that for us, and it worked nicely. Yeah, and then the interesting thing is we were not the first to propose these ski slopes. Well, okay, we came up with it in 2011, but we didn't publish it until 2024. So I don't think you can claim
Wow, that
credit.
took a little while to write up, didn't it?
Yeah, it was kind of a joke at first. Like we were at this meeting in Durham, and we were like, you know what? We need bottom heavy and top heavy. Then everybody will be happy.
Hey,
And it's like it was just sort of a facetious thing back then. But yeah, here we are.
funny how yeah, it works out some 14 years.
Yeah, no, it is interesting, but it's always been in our mind, and it was nice to actually write it up. But anyway, there are other studies, completely different angles
Yeah.
that have also proposed this. I'll just give one example from this list here.
Okay.
People have measured the X-ray binaries in elliptical galaxies.
Okay.
Yeah, okay.
Okay.
X-ray binaries. And what those are actually stellar remnants. That is, they are left over after supernova explosions,
Mhm.
and very dense objects. And what that measures is effectively the high mass end of the IMF. You can measure that at redshift zero by measuring the number of remnants. If you have a more top-heavy IMF,
Okay.
then you produce more remnants today
Okay.
than if you had a less flat IMF at high masses.
Cool.
So what
Okay.
they found is that it is actually consistent. The best fit was for an IMF that is a bit flatter at high masses. So they found too many X-ray binaries than expected from a standard IMF.
Okay.
Not by much, but by a little bit. And so there's all these funny sort of oldish results. This is not that old. That already pointed in the same direction. And
Correction.
so that's this concordance idea that it seems to solve a lot of problems. This IMF, it really
Nice.
helps, with a whole bunch of things. And then we go to tests. What we propose this thing and how can we test it?
Yeah.
Uh,
It's a good thing to do. Be able to test it.
yeah, and the nice thing is there's going to be a lot of JWST data, even just in cycle 3, already
Yeah.
approved programs that will help with this. And first of all, people will measure more and more dynamics with JWST of early galaxies. And again, the dynamics give you not the full picture because you have gas and dark matter, but they give you a limit. They will
Fair.
definitely give an upper limit to the
Fair.
uh, to the amount of mass that can be in stars. So that will come. That continues to roll in those kinds of data. Also, we are measuring the IMF in nearby elliptical galaxies better because there's a feature that is very strong in low mass stars and unobservable from the ground, and that is water. So water is a molecule that forms very easily when the gravity is high. And
Yeah.
so in these low mass stars, they're very compact, much higher surface gravity
Oh,
than
oh. Okay.
giants. And so you can count those stars by looking for the strength of the H2O water absorption
Gotcha.
in the atmospheres of
That's
those
cool.
stars.
That's very
Very
cool.
cool.
Nice.
And from the ground, it's very hard or impossible because our atmosphere has a lot of water, as it turns
Surely.
out.
Yep, it surely does.
So yeah, we have a JWST program that actually measures that and in this cycle, water in these nearby elliptical galaxies.
Nice.
So that's fun. And then there's another program by Mariska Creek, which I'm not sure I'm mentioning right there. And she's gonna measure the IMF in the same way as we've done at redshift zero from these more standard gravity sensitive features
Uh-huh.
at redshift zero point 0.7. So for the first
Okay.
time measuring the IMF more or less directly,
Cool.
at earlier times. So there's tests that are coming. And then we have physics. The referee for this paper was Mark Krumholtz, who is a fabulous physicist and has published many papers on the IMF and the physical origin. So he would not let this paper be published without a proper discussion
Without
of
even a
it.
speculation.
That's right. And you know, we had some things in here, but he also helped by pointing to some key papers that we had missed. But the essence is what we think is happening, but this needs, you know, much more work, is that we have these two regimes, the low mass regime and the high mass regime.
Right.
And what could be happening is that the low mass regime is set by the gene's mass, like the gene's
Okay.
mass being very low in these galaxies. And
Mm-hmm.
that could be because they're incredibly dense. So gene's mass depends on density and temperature. And what people have been finding is these little red dots, you know, which are, you know, ludicrously dense. They can't barely be resolved with JWST. You
Right.
know, the more compact than any sort of massive galaxies that have ever been observed,
Right.
and implying huge densities. And so that would lower the gene's mass, you know, sort of even
Why?
more lower
Mm-hmm.
everything else. But in isolation, that would lower the gene's mass in the expected way. And maybe the high mass regime is set by a different process, such as turbulence,
Turbulence, Mach
which
numbers. Yeah.
that's right. That has a big effect on the mass as well. And so perhaps there's two physical mechanisms that sort of compete with one another. And then in these particular very rarefied environments, this happens to be the outcome of those
Yes.
competing
Yes.
effects.
Yes.
And another option, that's the next paragraph, is sort of a different kind of idea. Is that the IMF, what we're seeing is the IMF after the whole galaxy has formed, of course.
Yeah.
You know, but it could be that different regions of the galaxy have different IMFs. So
Ooh.
maybe the center is very bottom heavy, you know, and
Uh,
that's in these very dense regions. But then at later times or at larger radii, you had star formation that was maybe more normal or even top heavy.
yes.
And so what we are seeing is this galaxy integrated IMF
Correct.
effectively.
Right.
And so we should always keep in mind that it could be that that's just a combination of different IMFs, but either over time or in space.
Space. Yep.
And again, we're not the first to say that. There's a whole literature on this.
Oh yeah.
Yep, Hoopa and others have talked about this for many years, the integrated galactic IMF. And again, some of these hybrid IMFs that they have proposed actually look quite a bit like the IMF that we find here.
The Concord.
So
Hmm.
from theoretical grounds, very different than these genes mass and Mach number models, but
Yeah.
also leading often to these kinds of ski slope shapes. Um,
Cool.
Now, and then at the end, or the next paragraph, and this was actually something that Mark suggested, which is absolutely right. It would be fabulous if we could see this by counting stars in some nearby star forming region. You know, this is kind of also if you would ask about future work, this is something I'll mention. The 30 Doradus cluster in particular is very
Yes.
extreme compared to other clusters in the local group,
Mhm.
and it has this high mass slope that is very similar to what we derive. You know, we
Yes.
derive 1.85, and the value that was derived by Schneider is 1.9. You know, with a big error bar, but still, it's essentially the same. And so it should be
Yeah.
possible, I think, to count the low mass stars with JWST in that cluster as well, to see if it has that upturn at low masses. But that would be the clincher. You know, if you can see this IMF in a star cluster, okay, then we know it's probably right. But anyway, it hasn't been done, and I'm not 100% sure it's possible. But then the most important thing we say at the very end, as a final remark, and we say that people always, you know,
Yeah.
IMF to solve all sorts of problems.
All problems can be solved by twisting your IMF.
Yeah, real or imagined. And yeah, so we are very aware of the
Yeah, yeah.
pitfalls, you know, of picking something that solves your problems by changing things that are very hard to observe.
Yeah, we'll come back to that here in a second. So very cool. Very cool.
Yeah,
Well, Peter, beautiful work. Beautiful work. And I
thank
want
you.
to thank you so much for walking us through your very awesome APJ letter.
Yeah, you're welcome. It was a
Yeah,
pleasure.
you certainly touched on it a little bit there on the future. There's lots of exciting possibilities. So it'll be really fun to see this field develop over, let's say, the next 5, 6 years over the next decade or so. Um, um, but it's also really, really cool that the IMF can be tested, right? That
Yeah,
it'll see, the slopes might end up being a little different or whatever,
yeah.
but the general form of those three power law things will be very interesting.
It is also, a lot of astronomy is discovery, right? We don't know what we're going to get. We turn on a telescope, JWST, and
Yeah,
we see
little
what
red
we
dot.
get. And then we find a little red dot, and we're like, what's that? How can we understand it? What we don't do very much is hypothesis testing, right? We have a hypothesis, which is, the IMF has a particular shape, and then we devise a test and we perform that test and we have an answer.
Hmm.
And I have to say that this particular field has been very satisfying from that perspective. It's like sort of real science,
Yeah, right, exactly.
following the scientific method.
Hypothesis test, yes, yes. Well,
Yeah,
it's
and
all
it's
Peter.
great.
Well, maybe it's group debt. Well, maybe it's concordance.
Yeah, so now we're turning it into this big mess. But initially, the initial question was, is the IMF universal? Right? Is it the Milky Way everywhere? And
Right.
that is a very clear falsifiable hypothesis. Because if you find it's not universal, if it's different anywhere, you've already falsified your hypothesis.
Right.
So now we're in this regime where we say, well, it has this particular form, these particular regimes, but it remains a prediction that can be tested.
Hmm.
And so that is it's nice. It's an important topic that is tractable, difficult but tractable.
Very cool. Well, I'm glad your musing 14 years ago or whatever it is finally come to this. We can test it. Awesome.
Yeah,
Very
we've basically been testing that claim in Nature in 2010 for the past 14 years. Yeah, and which means, of course, that we cannot be objective anymore. That we also have to recognize.
You have a bias, I am, of
Oh my
course.
God, for sure. We try not to, that's the thing. Like if the JWC data now show, like, oh, we don't see the water feature, what does it mean? Will we write that paper that say, okay, apparently we were wrong for 14 years. We would then still, the thing is, we would still have to explain all the other observations that we've done that indicate that the IMF is bottom heavy in elliptical
Right,
galaxies.
right, right, right.
But much better if other people do it, and they have. And so far, other people who've done similar tests that we have done have come to the same conclusions that it is bottom heavy in ellipticals.
Nice. And I like the fact you named it Concordance. I think that's a great, great name for it.
Okay, good. Yeah.
Very cool. Peter, I want to thank you so much for walking us through your very lovely APJ letter again. Thanks.
Yeah, you're more than welcome.
And
Yeah.
that will, that,
Yeah.
okay,
Happy.
cool. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.